All right, 2.8 is the last section in the chapter here. So we've already introduced the derivative in the last section, and we're going to talk more about that essentially. The derivative as a function. So the first derivative of f with respect to x, or f prime of x, is this limit definition. Okay, memorize that. We're going to be using a lot coming up here. Now, there's some derivative notation that we'll have to be familiar with in the book. So the f prime notation I've already talked about a little bit. That's going to be probably the most common notation that you'll see in this book. Now, not all functions will have function notation. In other words, you could have an equation in terms of y and x, all right, and you still have a function, you know. And y prime would be, still representing the first derivative there. Dy dx, or the first derivative of y with respect to x, is how we would read that. This is sometimes called Leibniz notation. Leibniz was a famous mathematician that was a key contributor in the development of calculus, and so this was notation that is named after him. You'll see that in the book quite a bit, okay? And then if you have function notation, the derivative of f with respect to x is how we'd read that. And then there's notation, the derivative of a function with respect to x, you just write the function inside the brackets there. Okay, so now all of these different types of notations you'll see in the book. They all mean the same thing. You're talking about the first derivative. Okay, let's take a look at an example here. So suppose we have the function f of x equals x cubed minus 5x squared. And we want to find the first derivative of f with respect to x, or f prime of x. Well, I'm going to start by writing the limit definition here. Okay, and f prime of x, f of x plus h would be where I replace x with x plus h, and I've done that. And then I'm going to subtract f of x. F of x is x cubed minus 5x squared. Put parentheses around that since you're going to be subtracting the whole thing, and you want to distribute the negative there in the end of the two terms. I'll do that on the next line. And of course, this is all over h. I'll need to simplify this first term. I've done that kind of on the side here. So you'll FOIL this part out and then distribute x into these three terms, distribute h into these three terms, and you'll collect your like terms then. So we have x cubed, and then 2x squared h plus x squared h, that'd be 3x squared h, and then xh squared plus 2xh squared, that'd be 3xh squared, and then plus an h cubed at the end, right? You'll have to FOIL this out. X plus h times x plus h is x squared plus 2xh plus h squared. Distribute the negative 5 into those three terms, and then also distribute the negative 1 into these two terms. Okay, and now we'll have some things canceling. X cubed minus x cubed, those are gone. Negative 5x squared plus 5x squared, those are gone. And the only remaining terms here are ones that involve h. None of these are like terms, by the way. And so, but h is in common to all of these terms in the numerator. You can factor an h out and cancel it with the one down under. Of course, I can't plug in 0, initially there, so I'd want to factor h out and cancel. And so now I can plug 0 in for h. This is a function of h, the limit that is. And so I'll go ahead and replace h with 0. And we get 3x squared minus 10x then, okay, since these other terms would be 0. All right, and so that'd be my answer. That'd be the first derivative of f with respect to x. Now, what if I want to calculate the derivative of the first derivative of f with respect to x? We call this the second derivative, okay? F double prime of x means that you're going to differentiate the first derivative, okay? Here's some common notation that you'll see in the book. Okay, so f double prime of x means that you're talking about the second derivative of f with respect to x. Okay, if you have an equation in terms of y and x, y double prime would mean the second derivative of y with respect to x. Okay, and then here's Leibniz notation. The way that we'd read this is to say the second derivative of y with respect to x. Notice the positioning of the 'to's there. That's positioned correctly. And now all three of these things mean the same thing. Okay, you're talking about the second derivative. So I had f of x, like in my last example here, I had f of x equal x cubed minus 5x squared. The derivative, we just calculated right here, that was 3x squared minus 10x. Okay, now what if I want to find the derivative of f prime of x? Well, that'd be the second derivative, right? F double prime of x. Well, I'm going to still use the limit definition there, the limit as h approaches 0 of the difference quotient. Now here's the thing. I'm differentiating the first derivative, so I want to make sure I'm using f prime notation here in the difference quotient. I want f prime of x plus h minus f prime of x all over h. Well, here's f prime of x. So where I see an x and f prime, there's two of them, I need to replace those with x plus h. And then subtract f prime of x, include parentheses around that since you're subtracting the whole thing, and you're going to distribute the negative into those two terms there. And this is all over h. Okay, now again, I can't plug in 0, right? So I'm going to have to algebraically manipulate the inside there. Let me FOIL this part out and then distribute the 3 into the 3 terms. Also, let's distribute negative 10 and then distribute the negative 1 into these 2 terms. Okay, and here's the next line then. So now I'm going to have some things canceling. 3x squared minus 3x squared is 0. Negative 10x plus 10x is 0. And I'm left with only terms involving h in the numerator. I can't plug in 0 still, but I can factor out an h out of these 3 terms and cancel it with the 1 down under. Okay, and so that's what I've done in the next line. And now I can plug in 0 for h. So I'm getting 6x minus 10 when I plug in 0 and lose the limit notation there. All right, now with the third derivative, you would differentiate the second derivative. F triple prime of x would be notation that you would use there, or y triple prime if you have an equation in terms of x and y. Here's Leibniz notation again. So the way that we read that is the third derivative of y with respect to x. Okay, and notice the positioning of the 3's, just like the positioning of the 2's. That's positioned correctly. All right, the fourth derivative notation. So once you're past the third derivative, we don't use tick marks anymore. We just write the number in parentheses. Okay, so the way that we would read this is to say the fourth derivative of f with respect to x, or the fourth derivative of y with respect to x. Okay, here's Leibniz notation, the fourth derivative of y with respect to x. These all mean the same thing. Okay, now a note with this, it may sound like a little thing, but it actually does matter. Make sure that you have the parentheses around the 4. If you don't, it looks like you're raising a function to the 4th power, which we are not doing. Y to the 4th would be raising this expression to the 4th power. I'm not doing that, right? I want to find the 4th derivative. So if I didn't write parentheses, it looks misleading, and so just a little note there. Make sure that the parentheses are there to indicate that you're talking about a derivative and not a power. The nth derivative notation then, again, if you're, whatever number derivative you're on, if it's something that is more than the third derivative, you're just going to write that number there inside parentheses. Okay, so here's the nth derivative of f with respect to x, the nth derivative of y, the nth derivative of y with respect to x. These all mean the same thing. Okay. let's go back to my my example that had started with up here. So f of x is x cubed minus 5x squared. F prime of x is 3x squared minus 10x. F double prime of x is 6x minus 10. We've done that already. Okay. And so how about, what if we wanted to know the third derivative of f with respect to x? Well, I could apply the limit definition if I want, or I could just go right to the answer and say it's 6. Because remember what we mean by the derivative. The derivative is describing the slope of the graph at a particular value, x. Well, if I have y equals 6x minus 10, that would be a line. This line has a slope of 6. Now, it's not going to matter where I'm at on the line. The line always has a slope of 6, right? So it's not going to matter what x value you plug in. You're essentially saying that the slope of this graph is 6. Now, how about the fourth derivative of f with respect to x? That'd be 0, since, again, you're describing the slope of the graph, okay, of the, in this case, of the third derivative. Well, if you had y equals 6, that would be a horizontal line at a height of 6, right? And a horizontal line always has a slope of 0. Now, the nth derivative of f with respect to x, that would be anything that is 4 or bigger, is always going to be 0, right? So from this point on, you're always going to get 0 in higher order derivatives. Let's take a look at some problems in the book here. Maybe we'll just do one in this video. So problem number 2 on page 160 is a good problem that I want us to work through. So in these problems, we are going to use the given graph to estimate the value of each derivative, and then we're going to sketch the graph of f prime. Okay, so I had wanted us to do problem 2 here. Okay, and in my notes I've redrawn this curve, and I've written down these calculations here. All right, so here's our here's our curve for that I've got marked here. This is f of x. Okay, now we want to compute these the following parts. Now the answers may vary depending on your estimates, because since you're working with a derivative, really what you're doing is you're estimating the slope of the graph at that spot. Okay, now I don't have a formula for f of x. So I'm estimating, like I'm not going to know exactly what that slope is. Okay, so there's a little bit of flexibility here with the numbers. F prime of 0 would be describing the slope of the graph of f at 0. Well, if I were to draw a tangent line at 0, I'd want to estimate the slope of that line. Okay, now the line is slanted in the positive direction, so I know I'm going to have some positive number here. And it looks like if I were to continue drawing this line, it looks like it's starting at 0, 0, and maybe it might pass through the point 1, 6. So I'd have to go up 6 into the right 1. Okay, I'm gonna estimate that slope then to be 6. Okay, now if somebody were to estimate it to be 5, sure, that's fine. That's still reasonable. Or 6.5 or something, like we're still relatively close. Those numbers would be acceptable also. Again, we're estimating. The answers may vary here. Now, f prime of 0 is roughly 6, means that the point 0, 6 would be on the graph of the derivative. Okay, so I'm going to plot these points as I gather them from my estimations. Let's go to the next point here, or part B. F prime of 1. Well, here's 1 is producing a hill on the graph of f of x. So if I were to draw a tangent line for that graph, it would be a horizontal line. A horizontal line has a slope of 0. Now this appears that it's creating a hill right at 1. Okay, the hill might not occur until like 1.1 or maybe like a 0.9 or something like that. So I can't say with certainty that it'd be equal to 0, okay, but it's very near 0 if it's not equal to 0, right? Since you'd be describing something that would be very much like a horizontal line there. So what that means then is the point 1, 0 would be on the graph of the derivative. Okay, how about f prime of 2? So here's 2 on the original graph. What is the slope of the graph at that spot? Well, I'm going to draw a tangent line here and estimate the slope. So it looks like maybe this point here is at 2, 1.5. Okay, now if I were to continue drawing this line, it looks like maybe the line might cross this point here, 1, 3, I'm just estimating. So I would have to go up 3/2 and to the left 1. Since I'm going to the left, I'm going to have a negative, right? So negative 3/2 or negative 1.5 would be what I would estimate there. Okay, so 2, negative 1.5, that would be the next point that I would plot on the graph of the derivative. Part D, f prime of 3. Well, here's 3. Okay, now this line, this slope, is going to be a little bit flattened out than the previous one. So I'd want a number that is going to be probably bigger than negative 1.5. Okay, I was calling this roughly negative 1.3. If you were calling it, negative 1.4, negative 1.2 or something like that, sure, those are all fine. Okay, so 3, negative 1.3, that'd be that next point that I would plot right here. Part E, f prime of 4. Okay, here's 4, and it looks like this line is going to be maybe slightly more flattened than the previous one. So still slanted in the negative direction, so I was calling that roughly negative 0.8. Okay, so here's 4, negative 0.8 on the graph of the derivative. F prime of 5, so 5, the slope of the graph is going to be more flattened than it was at these previous numbers here. I'm calling that one roughly negative 0.3 for the slope. Okay, so here's 5, negative 0.3. F prime of 6. So at 6, it looks like we have a valley on the graph. And this tangent line here, if it's not a horizontal line, it's very near a horizontal line. Okay, so, for all practical purposes, it would be roughly 0 would be the slope of the graph there at that spot. So 6, 0 would be on the graph of the derivative. And then f prime of 7, okay, so let's see, we're going to be working with a positive slope again, something a little bit bigger than 0, right? There's not really a steep slant to this, so I was calling it roughly 0.2. Of course, you can maybe use some symmetry here and, 0.3, that's fine. All right, so here's 7.2, okay. And then, now they're not asking for it, but f prime of 8 would be, a little bit bigger than this number, since the tangent line would have a little bit steeper slant to it, maybe like a 0.4, 0.3 or 0.4 or something like that. Okay, and so here'd be, another point that I could plot. And so using these points, I can then draw my curve. That would be the graph of the derivative, or f prime of x. Okay, now again, answers may vary, but still the overall shape of the derivative would look roughly what you would see here. Okay, we're going to come down, create a valley, and then come up. We'll pass the x-axis there, okay, at, roughly 6, 0. Now, one of the things that I'm looking for, early on when I don't have all these points labeled and stuff, is hills and valleys, okay? So on the original graph, like here's a hill and here's a valley, okay? Well, that tells me that I'm going to have corresponding x-intercepts on the graph of the derivative, right? Since the output would be 0, I know that that's going to produce points where I'll cross or touch the x-axis. Okay, now that's not something you got to look for first, but usually, you know, in some of these other problems, that's just something that I'm looking for kind of early on. You know, hey, where are we going to cross the x-axis? You know, because those are obviously key points on the graph of the that would be on the graph of the derivative there.